Everyone, and welcome to this explainer. Right, so today we're unpacking exactly why the physical architecture of global AI data centers is undergoing just this massive, fundamental redesign. Like, if you think the current AI boom is just about, plugging in more and more GPUs, well, you're about to see how software has completely flipped the script on hardware. We're going to look at the literal physical reality of the AI factory and how a totally new generation of software is forcing us to rethink the whole shebang from the ground up.
To get there, we've got a pretty clear roadmap. We'll kick things off with the Agentic AI revolution, then look at the great hardware bottleneck that it caused. From there, we'll break down the new one-to-one ratio, walk through how they're actually redesigning the AI factory, and wrap up with the real-world impacts and risks. I promise we're going to break all this dense hardware jargon down into a perfectly logical story. Okay, let's dive right into this, starting with the software evolution that actually kicked this whole thing off.
Think back to, old AI. Your standard chatbots. You throw a question at it, the AI processes it one time and just spits out a single-pass answer. It requires very little orchestration. But the new AI, Agentic AI, is an entirely different beast. It requires incredibly heavy, complex orchestration behind the scenes to execute these autonomous multi-step workflows. We've basically moved from simple Q&A machines to software that acts way more like a digital employee, managing its own daily tasks.
Just to be absolutely clear on our terms here, Agentic AI means autonomous software programs that plan, execute multi-step workflows, use external tools, and, this is the kicker, they evaluate their own results. For our hardware discussion today, the thing you need to remember is that this behavior requires continuous, heavy code execution and just unprecedented data management. It's a completely different workload compared to just predicting the next word in a sentence.
And that brings us right to our next point. Because this incredible leap in software capability, it's triggered a catastrophic failure in our current hardware setups. To really understand the breakdown, we have to look back at the old golden rule of data centers, the 8-to-1 ratio. Traditionally, you would cram 4, maybe 8 high-powered GPUs on a single host CPU. The CPU would simply hand the prompt over, step back, and let the GPUs do all the heavy mathematical lifting.
But now, operators are staring at their analytics dashboards and asking a literal multi-million-dollar question. So why are these extremely expensive GPUs suddenly sitting idle? I mean, we are talking about chips that cost tens of thousands of dollars a piece doing absolutely nothing, while the entire system just grinds to a halt. The financial and operational stakes here are absolutely massive.
Well, the culprit is a phenomenon known as accelerator starvation. It's exactly like having 8 world-class master chefs standing around in a kitchen, totally stuck, just waiting on a single prep cook. High-performance GPUs stop processing because that single, overworked host CPU gets completely overwhelmed by thousands of tool calls and API pings. It leaves the GPUs literally starving for data, just twiddling their thumbs waiting for the CPU to catch up.
Let's move on and see how this builds, because the structural solution to this starvation problem is totally reshaping the industry.
The fix? The new standard is exactly 1-to-1. To eliminate these massive hardware bottlenecks and maximize task throughput, data centers are shifting to an equal ratio of CPUs to GPUs. In fact, in highly autonomous scenarios, architects are actually deploying more CPUs than GPUs. It's a massive, incredibly expensive rebalancing act.
And this brilliantly illustrates how the chips take on totally distinct personalities in this split system architecture. The GPU acts strictly as the mathematical engine, right? Processing dense neural networks and generating text and code. But the CPU, it's been elevated to the conductor and controller. It manages the entire control plane, breaks complex goals into smaller steps, decides which tool to call next, and coordinates the logic. They are now truly equal partners on the data center floor.
To really appreciate this, just consider the intense new workloads driving the CPU right now. It's handling massive thread concurrency, meaning thousands of parallel agents running all at once, along with constant tool and API integration. But the absolute heaviest lift here is sandboxed code execution. Think about it. The AI generates code, and the CPU has to instantly open a secure, isolated sandbox, compile the code, test it, and analyze the results automatically. Zero human intervention. The orchestration overhead is absolutely staggering compared to where we were just 2 years ago.
So how is this actually playing out? Let's take a look at how architects are translating this new ratio into physical changes.
Enterprise tech leaders are optimizing their total cost of ownership through a pretty strict 4-step process. Step 1 is workload profile analysis, basically evaluating their specific shift from simple chatbot to heavy agentic tasks. Step 2, identify accelerator starvation on the actual servers where GPUs are stuck waiting on CPUs. Step 3 is the big one, the massive redesign, where they place independent, high-core count CPU server layers directly alongside the GPU infrastructure. And finally, Step 4, balancing the network fabric. They need ultra-high bandwidth links so these expanded layers can talk to each other with near-zero delay.
Now, let's zoom out a bit to examine the massive ripple effects this architectural correction has across the entire global tech industry.
The practical implications here are, frankly, staggering. First off, we're seeing a rapidly surging server CPU market that is just upending global purchasing budgets. Second, hardware manufacturers are rushing out entirely new processor designs built with massive core counts, designed exclusively to handle that heavy load of agent sandboxing we talked about. And third, AI factories are fundamentally evolving. They're turning into these widely distributed systems with separate, dedicated racks used solely for agent orchestration. So, the crucial point is, this massive expansion comes with some really severe physical and logistical limitations. Adding all these high-performance CPUs pushes total electricity consumption and cooling demands entirely off the charts. We're also facing serious network saturation because the bursty, constant communication between all these chips can easily overwhelm traditional networks. Plus, there is incredible integration complexity in making sure all these chips sync up perfectly. And lastly, all this sudden demand is causing heavy hardware supply chain pressures globally, which threatens to delay a lot of these expansion plans.
Which really leaves us with a final, critical thought. As autonomous AI agents multiply, what is the ultimate physical and financial limit of our data centers? I mean, yes, we've solved the software bottleneck with this massive 1-to-1 hardware ratio, but space, power, and silicon, they're finite resources. Will the hardware supply chain be able to keep up with the limitless ambition of agentic AI? That is the multi-trillion-dollar question the tech world has to answer next. Thanks so much for joining me on this explainer, and keep your eyes on the architecture.